next lecture, we will start our discussion on space groups in the 3 dimensions. We have already developed all the 3-dimensional point groups and as well as the 14 Bravais lattices. Now, we just can combine these two to get our 3-dimensional space groups. So, we have 14 Bravais lattices and we have 32 point groups. We combine them to get 230 space groups. Now, we are not going to discuss all these 230 space groups, we will just discuss a very small fraction of it, but you will see that the development of these space groups follow similar lines as we had developed the plane groups. So, let us start with the triclinic lattice. So, I have a triclinic unit cell and let us start with no symmetry at all. So, and I am going to draw only a 2-dimensional view of it. So, this is my A axis, this is my B axis and my C axis is coming out. And as you know, triclinic A, B and C have no constraints, neither do the alpha, beta, gamma angles. So, if I put a motif, an asymmetric motif, we are using the symbol, but this time I am going to put a plus sign to indicate that this motif is above the AB plane. The translation B will take it here, translation A will bring it here, translation of minus B will bring it here. So, this is my pattern for this first space group. At this we will label it for now as P1. Now, suppose I add inversion to it. So, let us add inversion to space group, that P1 space group. So, where are going to be my inversion centers? We have inversion with a small circle, I am denoting inversion centers. So, corners as well as there will be inversion in the center. So, this is center is in the body centered position. Now, if I put an asymmetric motif above the AB plane, the inversion will take this below the plane and that I will designate as minus, and it will also change the handedness. So, I will put a small comma inside to indicate that I have now started from a right handed, it has gone to a left handed motif. The translations will bring it here. And this is how this pattern will look like, and this space group, let me call it as P1 bar. So, in fact, these are first two space groups which are simple in nature with very little symmetry, and as we also know that the inversion produces no constraints on the lattice. Now, let us take a next example I will take from the monoclinic cell. So, let us start with monoclinic. No constraints on A, B and C and no constraints on gamma, and let us say that alpha and beta are constrained to be 90 degrees and gamma no constraint. Now, I have two possibilities with the monoclinic. I have simple monoclinic and I have end centered monoclinic. Now, these two cells we have seen in the last lecture that I can add the following point groups 2 m and 2 by m. So, how many space groups should this generate? If I do a simple multiplication, well, it says that I should get 6 space groups. However, the total number of space groups that we will get are much more, and in fact, to be precise, I will get 13 space groups. We will see how. Let us start with a simple monoclinic with only a two-fold rotational symmetry, and let us say along the axis C. So, C becomes the unique axis. And C is coming vertically out. So, I have the two folds. So, if I put a motif here above the AB plane, the two fold will rotate by 180 degrees, bring it here, and then the translations will take these two at all the corners. So, you can see that if I consider this one out here and this one out here, this two fold takes them on top of each other. Similarly, between this one and this one, this two fold will bring them into self coincidence. Now, this I am going to give a notation P, this is the long notation P112. So, the capital P is for the 3-dimensional space groups primitive. Along A there is no symmetry, B has no symmetry, along C, which is a unique axis, as I said, has a two-fold rotational symmetry. So, therefore, P112 becomes the notation for this space group. Now, take another example of the simple monoclinic. Here I have, let us say the AB plane is the mirror plane. Now, how do I indicate a mirror plane on this? Because we are now doing things in 3 dimensions. So, the mirror plane is indicated outside this diagram in this fashion. This symbol tells me that this is mirror in AB plane. Let me put a motif out here, starting with above the AB plane, but this mirror will reflect this motif right down, vertically down. So, how would I go about indicating, because the two motifs are going to be on top of each other. So, what we will do is we will divide this motif into two halves. So, this plus and the right side half, basically we are saying this is the motif which is above, the left side will be the motif which is down, we will indicate it with the minus sign. Now, the mirror also changes the handedness. To indicate that, we will put a comma on the left half. Now, simply the translations can take both the motifs to all the corners. The notation for this would be P11M. Again, the C axis is a unique axis, because the C axis is the one which is perpendicular to the mirror plane. Now, let us consider, we will remain in the monoclinic, but let me consider now the end-centered monoclinic. So, end-centered monoclinic, let me consider with the only a two-fold rotational symmetry present. So, I have, and let us say this is A, this is B. Let us say the A face has the end-centered lattice point, and let us say that lattice point out here will be indicated like this, but these lattice points I will just say half to indicate that it goes up half by C by 2, and the two folds, let me put the two folds. And let us start putting the motifs in this. Motif above the AB plane, the two fold rotates it in this position 180 degrees, but remains above the AB plane. Translations will bring them here. But we still have another translation to take care of, and that translation is the centering translation. So, translation going from the, let us say, from the origin out here to the central, to the lattice point in the center of the BC face. Remember, the C axis is coming out, and how up it will go? It will go by up by C by 2, and therefore, this one when translated, essentially if I look at the translation vector, the centering translation vector, it is B by 2 plus C by 2. So, go half out here and then half along B and then go up half along C. As a result, the way to indicate this would be to say that half plus, indicating that this particular motif is halfway up as compared to the motif we started with. 180 degree rotation will take this and bring it here, and you can see that the same thing will happen out here, and 180 degree rotation. So, this is how the motifs are going to be generated. Let us try to analyze this pattern and see whether there is some other symmetry also present. Let me say that this is motif number 1. It rotates by 180 degrees, comes to motif number 2, and then the centering translation of B by 2 plus C by 2 takes it to the motif number 3. So, to summarize this, 1 goes to 2 through a rotation of 180 degrees, 2 goes to 3 by the centering translation B by 2 plus C by 2, and we want to find out how do I go from 1 to 3. Now, remember, there is no handedness change in any of the motifs simply because there are no reflection or inversion operations. So, how can I go? So, if we think about it a bit, imagine let us take a point out here. This point is basically 1/4 from the origin along B. If I rotate motif number 1 by 180 degrees, where will it go? It will go exactly below motif number 3. So, what I am doing? Rotate 1 by pi about this point, let me call this point as P, about point P. So, this goes just below, in fact halfway below, just below 3. And the second operation that we do is translate vertically up by half, and it will self coincide. So, therefore, this is an operation just like we saw a glide plane earlier. This is an operation which is a two-step operation. So, rotate by 180 degrees and then go up by half. And such a symmetry which has these two steps involved is called a screw axis. And since it is a 180-degree rotation, it will also be called as a two-fold screw axis. Let me try to show this in another sketch, the screw axis. Let us say this is a screw axis, a two-fold screw axis. And so, let me start with an asymmetric motif. Rotate by 180 degrees, I come here, but then I do not leave it here, but I go up, and I go up by C by 2, and basically this comes out here. So, I should not leave it here, so I will remove it. So, basically 180-degree rotation and then go up parallel to the axis to position 2. Similarly, I rotate another 180 degrees, it comes here, but then I go to a new location 3, and this is also C by 2. So, 1 to 2 rotation of pi followed by translation of C by 2, 2 to 3 rotation of pi followed by translation of C by 2, 1 to 3 clearly is simply a translation vector C. So, C becomes the lattice translation vector. So, therefore, for a two-fold screw axis, the translation component would be exactly half the lattice translation, but this is not going to be true for other like the 3-fold or the 4-fold or the 6-fold. We will discuss that later. Now, another thing, the symbol that we use for the screw axis start out like a 2-fold, but we have these little fins to indicate that this is a 2-fold rotational symmetry. Now, going back now to the previous diagram, now insert the screw axis in this diagram of the space group. So, I will have the screw axis out here. Similarly, I am going to have it here. The translations will also bring the screw axis out here. And if you notice, let us say between 1 and 4, how do we go from 1 to 4 and 4 to 1? There is going to be a screw axis out here, there will be a screw axis out here. This completes the this particular space group diagram. Now, what will be the notation that I would use for this diagram? Well, first of all, the first letter has to indicate whether it is a primitive lattice or it is a non-primitive. In this case, it is an end-centered, and hence end-centered, also the centering face is the A face. So, it starts with A. Again, it has no symmetry along A and B. So, 1 1, and then I had added basically the two-fold along the unique axis C. So, it is A 1 1 2. Now, before I discuss the screw axis further, I want to take another space group, again based on the monoclinic system, in fact on the end centered monoclinic. So, end centered monoclinic means that I have, let us say again the lattice points in the center of the A face, and let me not consider the, let me consider this time, let us consider the end centered only, lattice point in the center of the A face, but this time instead of having a two-fold, there is a mirror in the AB plane. So, I have already seen this for the case of primitive. Now, this is the end centered. If it was primitive, it will be, if you, this one out here, P11M. So, I had put for the primitive, there is a, the mirror is in the AB plane. Here it is end centered and the mirror is still in the AB plane. So, I will have so, I have these motifs distributed like this. This is only the primitive part, but now I have to consider the centering translation of B by 2 plus C by 2, and therefore, this motif will move out here. This will go half plus handedness change and half minus. Similarly, translation of B will bring this here, half plus and half minus. This is the way the pattern would look like. Now, consider, we have to now analyze this pattern to figure out whether there is any other symmetry present or not. So, let us take motif number 1, which is right handed above the AB plane. The mirror takes it to motif number 2, left handed below the AB plane. 2 is taken to 3 by centering translation of B by 2 plus C by 2. Handedness remains the same, left handed, and it has gone to a position half minus. So, if I summarize this, 1 to 2 was sigma, 2 to 3 was B by 2 plus C by 2 translation. One to 3, how do I go from 1 to 3? Well, this is something that probably you would be able to guess if you think about it a bit. Maybe you can pause the video here, think about it before looking for the answer. So, going from 1 to 3, there is a handedness change and there is a translation involved. Clearly, that is a glide plane, just like what we had seen earlier. 2 steps, reflection and translation. So, 1 gets reflected down to minus position and then centering translation moves it to the position number 3, and in the vertical position it becomes half minus. So, there is a glide plane here. Now, where is the location of the glide plane? So, the glide plane has to be between the motifs 1 and 3, and in fact, it will be exactly 1/4 along the C axis above the AB plane. So, that glide plane, how do I represent this? Well, I represent it like this, and it is 1/4 above. So, I also have to write down 1/4 to indicate that this particular glide plane that I am talking about is 1/4 along the C axis above the AB plane. This arrow that is drawn, so it is like a mirror, but then there is an arrow put. This arrow is indicating the direction of the glide translation, which is along the B direction, and exactly it is B by 2. If I look for the notation for this particular space, so first of all, it is an A centered lattice, nothing along A, nothing along B, and we had put a mirror plane. So, A11M. So, I have introduced the screw axis and I have put a mirror plane to it, and now when I said that I get so many space groups from a monoclinic system, well, now what I can do is I can simply add a screw axis to a primitive monoclinic. I can add a glide plane to a primitive monoclinic to get couple of more planes. So, let me just quickly do this. Let us take a primitive monoclinic and add a screw axis instead of a two-fold axis. And in the center also there will be a screw axis. So, only two-fold screw axis, no pure two-fold axis is present. And if I put the motifs in this, so let us say motif above the AB plane goes to A half plus, and the translations will take me to all the corners. Now, what should I call this space group? Well, it can be called as primitive to start with, then 1 and 1 along A and B. But now, along the C, the unique axis, there is a two-fold rotational symmetry. So, I will need a symbol for that as well. Well, the symbol for that would be, so if I come back here, what symbol should I put? The symbol 2 sub 1 is put. Now, I will explain the logic of this symbol when we discuss the screw axis in more detail in the next lecture. And one final thing before I complete, let us add a glide plane to a primitive monoclinic. So, this is my primitive monoclinic cell, and I add a glide plane. Now, since I have written no fraction, no number along with this, which means that this glide plane is in the AB plane. So, motif above, motif above the plane is translated to all the corners, and we now also have to apply the glide translation. So, starting with this first motif in the top left, we reflect, it goes down and then translate by b by 2. So, it becomes left handed and below the AB plane. Similarly, out here, how the pattern will look like. The notation for this is P primitive 1 1, and now I can't write M because this is a glide plane. So, I have to have another symbol for that. Well, this is a glide plane whose glide translation is along the B axis, and therefore, I will write the letter small b. So, small b indicates B glide. Whenever you see these small letters like A, then it will be in the direction of A, C in the direction of C. There will be other symbols as well like N, you might even see an N glide. We will discuss all that in the subsequent lectures. Now, with this I conclude the lecture, and we will continue this in the next lecture. Thank you.